In this video, we're going to use Simpson's rule to help us approximate an arc length. So the problem asks us to use 10 subintervals and Simpson's rule to estimate the length of y equals e to the negative x squared on the interval from 0 to 2, and then it asks us to compare our answer with what we get if we plug it into a calculator. Well, if our function is e to the minus x squared, our derivative then would be a negative 2x e to the minus x squared. So under the radical, we get a 1 plus 4x squared e to the minus 2x squared. That would be very, very difficult to try to integrate that by hand. However, we do know what our f of x is now. Our f of x is our integrand. You remember using Simpson's rule, we use 1/3 delta x, and we calculate delta x as the difference of your limits of integration divided by the number of subintervals, or better said, b minus a over n. So we get 1/5 there, if you want to simplify it. And then remember, we plug in each of our points. So instead of delta x is 0.2, then 1/5. Our points will start at 0, because that's the left endpoint, and we'll go up by 0.2 each time until we get to 2. And then remember, our coefficients on f in the sum alternate 4, 2, 4, 2, so on, 4, except for the first and the last ones. Those are just a coefficient of 1 in both of those. If you go through and plug all those values in and add it up and simplify, or I should say approximate, we'll get 2.28056 using Simpson's rule. And if you put this in a calculator, here's a screenshot from doing this on a TI-83, an old TI-83, but you can use any calculator you want that has integration or numeric integration technology in it, and you'll get approximately 2.28053 as your approximation. So we see here, using 10 subintervals in Simpson's rule is a pretty good approximation to what the actual value of the integral is, since it's really, really close to what the calculator is giving us as an approximation.